Cevabını çok iyi biliyorum ben. 5 dakika ileri alabilir miyiz arkadaşlar? Yok.
Evet, hayır diyenler desiniz hocam.
Bir kişi bir ithal derse değiştiremem ki. Ben bu dersi bu yüzden aldım, şimdi böyle yapıyorsun. Hemen gidip valiye şikayet yapalım.
Hocam bir dinleyiciyi kaydıracaktık. Adam bir saat fazla beklememek için hayır dedi.
Evet doğru. Ama yani yalanın sonu yok ki, başka neler çıkarıyor. Hastaneden rapor getiriyor, annem benim hastanede yaptı. Doktora da yalancı biliyorsun. Yok yani dersin yerine oynatmanın şeyi yok. Başlangıçta biz ne koyuyorsak orası oldu. Yani çakışmasıyla beraber ben bunu bu şekilde aldım. Tamam böyleydi. Yeni değiştirdiği zaman başka bir şey çakışacak. Onunla çakışmasıyla bununla çakışmasını tercih ediyoruz diyor. Falan. Bu arada yarın dersi ben yapacağım. Çünkü geçen hafta 2 saat yedim ben. Yarın 1 saat dersi ben yapacağım. Çarşamba günkü dersi de ben yapacağım. Bu hafta 5 saat quest. There was a question during the break. The question was about, remember with the Windows operating system, all the graphical user interface stuff was handled in the kernel space. That's why we said that it is more efficient to handle everything in the kernel space when we are doing the graphical user interfaces. So how come handling everything with the thread-related stuff in the kernel space is less efficient? So when we do the graphical user interface, the GUIs, inside the kernel space, it is efficient. But when we are doing the threads inside the kernel space, it is less efficient. That was a very good question, actually. The thing is that the inefficient thing here is that switching between the user level and the kernel level modes, okay? If you switch too often between the user level and kernel level, then that's inefficiency. If you draw your windows pixel by pixel by asking the operating system, now draw this pixel and draw this pixel and draw this pixel, it is much less efficient than asking the operating system to draw the window itself. So with the Unix, with the Windows, you ask the operating system to move the whole window from one part of the screen to another part, and it is done by the kernel level routines. So it is less number of switches between the kernel level and user level with the case of the Windows. But for the Unix, you have to do lots of stuff yourself, so it is less efficient because you need to ask the operating system many things. The same thing happens here too. You need to ask the operating system to do many things. There is no other way of asking the operating system to handle all the thread processing stuff at the same time, because you are writing your program yourself. So you need to write code like that, right? Your code is like this, okay? Okay, you make a system call, and another system call, another system call. So you cannot make all of your system calls at the same time. You need to switch back and forth. This is not the case with the user interfaces. With the user interfaces, you usually do one thing. You say that, okay, move this window from this part of the screen to the other part of the screen. And this is a very complicated thing, and it can be done in the kernel space in a very efficient way. So you are making just one simple system call. Again, it is expensive, but it is just one call, and it is done efficiently. Once you are in the kernel mode, it is efficient, but switching between kernel and the user mode is inefficient. And with the threading libraries, we have to switch between user and the kernel modes a lot if you are doing your thread handling with the kernel mode. Okay, so let's talk about this blocking system calls and page faults. Blocking system calls. So let's say if we get some help from the operating system, not direct help about the threads, but some help about blocking system calls, okay? If a thread says that, okay, read, okay, I'm going to read some disk and read them into the memory, and there is no data available, the kernel will make the whole process block because it is unaware of the thread structure. It doesn't know there are more than one thread is running because it is implemented in the user space. So that means that there is an inefficiency, difficulty issue in user level threads, and we need some help from the operating system. Otherwise, my whole process blocks and I lose my interactivity of my application. Okay. the same problem with the page faults. We didn't look at the virtual memory yet in detail, but we will study it very carefully. When there is a miss for a memory reference, that memory needs to be loaded from the disk, and the problem becomes exactly like this one, like the read case. The whole process is blocked due to the problem with one of the threads. Okay, so to handle this problem, blocking system calls, one solution is to get some help from the operating system. Says that, okay, before making a call, let's say a read call to the operating system, there is a call that called will block. Okay, before making the call read, you would ask the operating system, if I make this call, would it block my process? Okay, operating system will tell you that it's going to block or not. If it is not going to block, you make that call. Okay, you make that decision. Okay, I'm going to call this, and because it will not block, I can continue running my thread. If it's going to block, then you might decide that, okay, I will yield first. Before making this call, I will yield first so that other threads can continue and complete their tasks. When the execution comes to me back again, okay, then I can make this call because all the other threads have completed their jobs and nobody is waiting for the CPU in my thread. So some little help from the operating system. You ask the operating system if my call is going to block. Okay, the operating system still doesn't know if you are running a threading application inside your process. All it provides is this one, will block system call. Another one is that some operating systems no system call blocks. Okay, when you call read, if the data is available, it returns the data to you. If it's going to block, it says that, okay, I am returning back to you. I am not going to give you your data. It will be ready in 100 milliseconds, but I am giving execution to you again. You can do anything you want. In this case, when the operating system returns from the execution saying that the data is not ready, then I can say, okay, I will wait here. I will yield to other threads, and I will wait until the data is ready. So only one of the threads is waiting, the others are still continuing. So these are some of the solutions to this. Blocking system calls and the page calls. So you get operating system help. Without the help from operating system, these two issues are very serious issues. Okay? Any questions? These are the, again, user level threads. Let's go back to kernel level threads, talk about them. In the kernel level threads, we have the kernel managing the thread. So we have some serious support from the operating system to create, destroy the thread, and the originating thread makes the kernel call. Whenever you need anything from the threading library, you make a operating system call. Similar thread table, all the information about the thread, the stack information, all the registers, and etc. You have the table, but the table is in the kernel. Okay, the table is in the kernel; it's protected. Nobody can access to it directly, so there is no thread level crashes due to the unwanted effects of modifying memories, other people's memories. Okay, so it is often integrated with the process table. The process table is already in the kernel, so you associate this thread table with the process table for each process. Okay, no problem with blocking system calls, because if one thread blocks, the operating system can run the other threads. So there is no problem with the blocking system calls or the page faults and etc. And one of the most important advantages of kernel level threads is the multi-CPU. Since operating system schedules the CPU assignments, okay, say that, okay, thread 1 will use this CPU, thread 2 will use this CPU, and process number n will use the other CPU, okay? So it can do this very, very easily, handling the multi-CPU cases. I cannot do this with the user level threads, okay? But again, thread switching is expensive since it needs context switch, okay? It needs context switch. And context switch is expensive because we are using virtual memory and cache and that kind of most of them efficient stuff. Those efficient stuff, virtual memories and the caches, they are very efficient if there is a single program running inside the operating system. But if you switch between two processes all the time, back and forth, then context switching becomes very, very expensive. And in this case, when you switch from the user mode to the kernel mode and back to user mode again for each system call, then it becomes a problem. But again, you might ask that if kernel level threads are so expensive to use, how come we don't use the processes instead? Why are we using the threads? We are using threads because they are 10 times, sometimes 100 times faster than the processes, right? Creating a process is slower. Switching from process to process is slower. Doing all kinds of process communication is slower than the thread. That's why we are using threads. If there is context switching with the kernel level threads, okay, how come we are not using processes instead of using kernel level threads? The answer is, even if you are using kernel level threads, they are still cheaper than process switches because we are using the same virtual memory map. We are not changing our address space, okay? Changing address space is much more expensive. If you change your address space, then all of your virtual memory maps has to be reinitialized, and they are not they are in the memory, but they need to be sometimes written to the disk and brought it back, and this is much more expensive stuff. Context switch plus the virtual memory map switch is much more expensive. That's why it is more expensive to switch from one process to another process, changing the address space. Again, kernel level threads are slower than the user level threads, but they are faster than the process switching. Okay, so if you write 2 processes, 3 processes to handle your word processing application, it should be slower than any of those user level or kernel level threads. Okay, so it is slower than the user level, but it is still faster than the process switching. Okay, with the kernel level threads we have these problems, additional problems other than the inefficiency. Okay, what happens? Let's say if you call this system call fork to create a new process. Okay, then what does fork do? It copies it creates a new process with exactly the same copy as the calling process, right? So you make an exact copy of the calling process to make a new process. So what happens to the threads? Do I copy the threads too? Okay. So I copy everything, all the process data, stacks and everything, all the open files and the signals and everything. What do I do with the threads? Does the new process have as many threads? Okay. So the answers are dependent on what kind of parameters you are giving this to fork, and depends on what follows the fork. How about the signals? For example, the signals are sent to the processes, not the threads. Okay, when I send a signal to a process, does all of the threads have the signal? Okay, for example, a Control C signal. When I do the Control C, it means that break the current process, right? That's the default behavior. Do I send the same signal to all of the threads that is running inside the process? Since these are all handled by the operating system, in the user level threads, this is easy to handle because I am making all of my decisions myself, okay? My threading library is doing this. It is more flexible. But these kind of behaviors has to be handled by the operating system itself. So I need lots of parameters to deal with these kind of problems. Again, other than the inefficiency of the kernel level threads, there are some problems that needs to be addressed. And I'm not giving any answers to these problems actually. It depends on the case. It depends on the operating system. There are no definitive answers for these questions. Okay, any questions about the user level threads and the kernel level threads? Yes.
In what cases sending the threads to the new process will be useful instead of creating the threads in new process?
In what cases again? In what cases?
In what cases sending the threads with fork to the new process will be useful?
But the question here is that when you call this function fork, I have to copy everything inside my thread. Do I copy the threads too? Let's say I have 5 threads running. Should I copy all of them or should I copy? Okay, since I am running a thread inside my fork, okay, when I call a fork from one of my threads, the new process, should the new process copy all of the other threads or my single thread only? That's the question.
Yeah.
And it depends on the case. The answer is it depends on the case. And if you need all of them, then you need to ask the operating system, copy the original process with all of the threads too, okay? So you need to send a parameter to the operating system saying that I need all of the threads to be copied. Otherwise, you need to send another parameter to the operating system that says that I need only the current thread to be copied, not the others. Which makes this fork and many other operating system calls complicated. That's the issue here. So it depends on your problem. It depends on what follows the fork. That's what it's saying. The same problem exists in the user level threads, but user level threads are libraries, so I can do whatever I want with my library. But with this one, see, I am changing behavior of my usual process handling functions because of the complications that come with the threads. My operating system is becoming more and more complicated. That's what it is saying. So it is not as simple as I am adding multi-threading support to my kernel. If you add this support, then there will be other problems, and you have to solve those problems too, which makes your operating system more complicated. Okay. So let's look at some other ways of handling these issues. Some hybrid approach. Okay. Some hybrid approach says that let's stay in between. I mean, I get some help from the operating system, but I do most of the stuff in the user level threads. Okay, I get some help from the operating system, and I do some stuff in the user level. So I am gaining some efficiency because I am running most of my stuff in the user space, but I get help from the kernel so that I don't have blocking system calls, I don't have page fault problems, or the multi-CPU handling problems. Okay, so this is called a hybrid approach. Some kernel level threads with each kernel level thread supporting several user level threads. Okay, again we have two others. Okay, one alternative is this one. The other one is schedule activation. Another one is pop-up threads, and we will check these two out later. Let's look at this hybrid implementation. This picture should be clear enough. In this case, the kernel supports the threads, but I have the user level threads too. Okay. I say that, okay, I have total of 1, 2, 3, 4, 5 threads running inside my process. 5 threads are running, but I say that I say to the operating system that these 3 threads will be run as a single kernel thread, and these 2 will run as a single kernel thread. Okay, So the kernel knows that there are two threads running inside this process P0. The kernel thinks that there are two threads are running, but in fact there are 5 threads. So switching between these 3 threads are very, very fast. Switching between these 2 threads are very, very fast. Switching between from this one to this one is kind of slow because these are run by the 2 different kernel level threads. So most of the time switching is very fast, sometimes it is slow. Okay, this is kind of in between solution. This is not as efficient as the user level threads, but it is not as slow as the kernel level threads. Again, if there is something happens, if this one blocks, okay, if this thread blocks, it blocks this thread too, but these 3 threads can go on. Why? Because these 2 are assigned to this thread, these 3 are assigned to this thread. If this one is blocked, if this thread is blocked, these 3 can still continue. So there is a partial solution for this blocking problem. There is a partial solution. Again, since the kernel thinks that there are 2 threads, it can assign one CPU to this thread, another CPU to this thread. So these 2 are running on CPU number 1, and these 3 are running on CPU number 0. So this is a again, I get help from the kernel, from the operating system. Operating system knows that I can have more than one thread inside my process, but there is user space thread handling too. In the user space thread handling, I can assign many threads to the same kernel level thread. So this is kind of best of both worlds. It's not the best, but it's kind of taking advantage of the both user level threads and the kernel level threads. There is still blocking issue. If this one blocks, okay, this one blocks, it will block this one too, but the others will continue, right? So only this one will get affected. And it is up to you. It is up to you how many threads to assign to this one, how many threads to assign to this one. It is your decision as a programmer. So this is called hybrid implementation. User level threads are multiplexed to the kernel level threads. Kernel is aware of only the kernel level threads and schedules those. The kernel schedules these 2, okay, time scheduling and everything, okay. The scheduling of these 3 and these 2 are done separately by the user level thread library in a very efficient way. Okay, any questions? So this is called hybrid implementation. Another one is scheduler activations. Again, it is trying to do the we get some help from the kernel, but it is not full scale help. It is not the full scale kernel level implementation. But we are using most of the stuff in the user space. So efficiency of user level threads and the non-blocking ability of kernel level threads, it uses this technique of upcall. Okay, what's an upcall? Upcall is this. Okay. Usually, okay, this is my hardware. This is my operating system, and this is my application program, right? So when I make a call to the operating system works on the call and it returns an answer, right? So the communication is this way. It is always like this, okay? And sometimes it goes down to the hardware and comes back. And it is always application starts something, it asks the operating system, and the operating system returns back with some kind of an answer. Sometimes it blocks the asking process application program. Sometimes it comes back immediately, but this is the usual way of doing it. With the upcall, it is kind of the reverse. Normally, user programs call functions in the kernel. Sometimes, though, the kernel calls a user level process to report an event. So, sometimes the operating system initiates some kind of a call to the application program. So, sometimes sometimes operating system says that, okay, something happened, okay, This is called up call. This is not downwards, but it starts from the operating system to the up. It's called up call. So some people don't like it because they say that unclean violates the usual layering. In the layering approach, the initiation starts from the top, it goes downwards and it comes back again. In this case, operating starts the communication initiation. Some people don't like it, but this is the solution to the user level, kernel level thread issue. In this case, what happens is that, in this case, scheduler activations, thread creation and scheduling is done at the user level. Okay, when you create a thread or when you do the scheduling, it is done at the user level, like it is done by the user level threads. When a system call from a thread blocks, okay, to solve this problem, we are going to use the opcode. The kernel does an opcode to the thread manager. Okay. I ask the operating system to load a page from the disk. Okay, and the kernel says that making an opcode to the thread manager inside the kernel space says that okay, your call is blocked, and I'm informing you about that. Okay. So it is informing to the thread manager saying that your thread made a call and it is blocked. So the thread manager has the control now. The thread manager marks that thread as blocked and starts running another thread. So that thread is blocked and I have another thread running. So the operating system is making, okay, one thread says that okay, read me a file. Okay, operating system took that call and it saw that that process or that thread is going to block, and it blocked the thread and it made an up call to the application program or my threading library says that okay, that thread is blocked because it cannot continue. Now the scheduler in the user space can start running. Okay, the thread manager can start running and it marks that thread as blocked and starts running another thread. Okay, using the up calls, I can do this. When a kernel interrupt occurs, that's relevant to the thread, another up call is done to unblock it. So when the data is ready, the operating system makes another up call to the thread that was blocked before, and that thread can run again. So the communication is not always from upstairs to the downstairs. Sometimes it is from downstairs to the upstairs. Kind of violating basic rule of operating system layered structure. But using this structure, I can make some decisions myself in the user space, because operating system tells me that your process, your thread is blocked because it asks something to be loaded from the disk. It's called upcode, and the method using those upcalls to handle the user level blocking, thread blocking is called scheduler activations. Your scheduler is activated by the operating system. Say that okay, your thread is blocked. What are you going to do? The scheduler says okay, I am going to run this thread right now. So you get from the operating system all the time whenever something blocks. Okay, another solution, in between solution between the user level threads and the kernel level threads. Scheduler activations. Okay. Any questions on upcalls? Without getting help from the operating system, I cannot solve this blocking thread problem. Okay? I need to have some kind of a help from operating system. The full scale help means that I implemented everything in the kernel space, which is inefficient. If I wanted to make a little bit more efficient, I am going to use either this hybrid implementations or other kind of implementation like the schedule activations. Whenever something blocks, operating system tells my scheduler or the thread manager, that something has blocked and maybe you can start running another thread. Without the help from operating system, I can't do that. Okay, another one, pop-up threads. Actually, we kind of looked at this, another version of this previously. Then we look at the threads. We do this with the, okay, we do this, what's the time? Should I? You know what, I'm gonna skip this one. You read this one from your book because I don't have time. I'm running, because I'm running out of time. I need to start the other task. You read this from your book. Actually, we kind of looked at this before. That's why I'm skipping it. And I'm gonna look at this issue now. Making single-threaded code multi-threaded. Any questions about anything before? Pop-up, schedule activations of calls, or the hybrid implementations? So what we are doing today we looked at user level threads, kernel level threads, and hybrid threads that is in between user level and kernel level. And I looked at two of the methods, and the third one is assigned to you. You are going to read it. So let's look at a little bit about from the programming perspective. How do I write multi-threaded code? Remember, we didn't talk about multi-processing code. I mean, if you write a process, it's a single process. You think that there is only a single process, and I have the whole CPU to myself. I can use the CPU all the time. I can access the disk, and everything belongs to me. Okay, I don't have to care about other processes. It is the task of the operating system. With the multi-threaded approaches, I cannot say this anymore because I should cooperate with the other threads that I am writing, right? I am writing all of the threads myself, and I cannot say that I don't care about the other threads. I write my code, and the rest of it is handled by the operating system. No, it is not the case because I am using the same address space. I need to be careful when I write multi-threaded code. Okay, so writing multi-threaded code takes some getting used to. Why? Let's look at this one. Local variables and parameters do not cause any trouble because whenever I call a function, when you call a function like this one, I have three integers. They have some values. I call this function A, B, C, okay? And this is inside main. So whenever I call this function, what happens? Tell me what happens. I am calling this function f. First the return address is pushed onto the stack. Then what else? Then
function.
What again? How do you make the copies of ABC? You push them onto the stack, right? You push them onto the stack A, B, C. You push them onto the stack, and then what? You start running this function f. If it has local variables, you create space for those local variables inside the stack too. So you do all of your local variables and parameters inside the stack, right? So if I have two different, let's say this is function g. This is function g. It returns an integer. If I run this function g, it has its own local variables and it calls something else. But it does everything with the local variables and the function parameters on the stack, right? Since each thread has its own stack, each thread has its own stack, that means that it doesn't matter how many threads I have. Everything is going to be handled just fine because all the threads, they have their own stacks, they have their own local variables, they have their own parameters. So having local variables and parameters do not cause any trouble in terms of multi-threading. But the global variables are a problem because global variables are shared, right? Whenever you use a global variable inside a function, whatever you do, it will be seen by other functions too, because they are global. So the problem is, if a thread makes a change to a global variable, other threads are going to get affected. Other thread is going to get affected, which becomes a problem. The problem is kind of here. Okay, let's say I have this error number. I have two threads. One thread is running. Okay, thread number 1 says that error number is ERR number is 1. Okay, so it set the error number to 1. Then we decided to switch from thread 1 to thread 2, and the thread 2 said that error no is 2 now. Okay, then I switch back to thread number 1. Thread number 1 thinks that error number is 1, but in fact it is 2, because since it's a global variable, whatever you change from this thread, it will be seen by this thread, which creates lots of problems, big problems when you use global variables. Okay, so one golden rule for the global variables is that do not use any global variables. We have been telling you for the last 2, 3, 5 years, for some of you, even 6 years. We say that don't use global variables, right? If you use global variables, for the object-oriented philosophy, actually, it is bad. For multi-threading programs, it is bad too. Don't use global variables, because with the global variables, since they are not stored on the stack, right? They are stored on the common memory that everybody can access, all the threads can access. When once you change it, the others will see it. So one solution is altogether don't use any global variables. If you are using a global variable, make it read-only. Making the global variable read-only is no problem, because nobody is going to change it, okay? You just read it. One solution is to prohibit global variables altogether. Another solution is, it is possible to allocate a chunk of memory for the globals and pass it to each procedure in the thread as an extra parameter. So it says that it's kind of make a new space, okay, a private space for each thread, and keep your globals inside this space. So each thread has its own global variables, so they cannot share the same global variable. So it made a new function named create global. Okay, this is create global. Create global creates a new global buffer. This is a private buffer for each thread actually. And when you set your global variable like this one, okay, set global and setting it to some value, and this is reading your global buffer. And the picture looks like this. Thread 1's code, thread 2's code, these are functions, simple functions. Thread 1's stack, and thread 2 stacks, and thread 1's global, and thread 2's globals. So the globals are stored in some other place inside the memory, and this way I don't have these kind of problems with the globals. Okay. If you wanted to use the same global, okay, you are saying that okay, I want this thread 1 and thread 2 to use the same global, so that if one changes this one, the other one can see it. You can still do it. Sometimes that's how we communicate between two threads. Inter-process communication or inter-thread communication. If this is what you want, then you can do it, but there are some problems with that one, and we will see it at the end of this chapter. Any questions? Soru sorun bir tane ya. Evet.
Hocam hani şimdi dedik ya burada thread 1, thread 2'de değişen global variable'ın haberi yoktu, yani hala error'unu 1 olarak düşünüyor diye.
Evet.
Daha deminki resimde nasıl çözdük onu? Hani mesela thread 1'inkini ve thread 2'ninkini
Şunu diyorsun, burada mı nasıl çözdük?
yok hayır. Bir şey vardı ya tablo, evet buradan.
Çünkü bunun globallarıyla bunun globalları artık farklı. Birisi error no deyince bir tane değişkene erişiyor. Öbürünce başka değişkene erişiyor.
Ama yine aynı şey olacak. Hani mesela o iki
Aynısı değişmiyor ama farklı yerde onlar.
Tamam, hani mesela şimdi thread 2 dedi ki global error no 2 dedi. thread 1'de error'unu hala 1 olarak sanacak yine.
İşte böyle kullanmayın diyor. Şöyle bir tane kendinize şey yazın diyor. Global'ları içeren bir tane buffer alın diyor. Tüm fonksiyonlara diyor. Hani parametre yolluyoruz ya fonksiyonlara.
Evet.
ABC yollamıştık ya. Global'ları içeren bir tane de struct daha yollayın diyor. Her birinin kendi şeyi olsun diyor. Global olsun diyor. Global'lar sanki lokalmiş gibi. Bak şurada esasında birazcık şöyle. Şunu birbirine bağlamış, gördün mü? Stack ile global'ı. Sanki stack'in en altında global'lar varmış gibi. Bu da bunu birbirine bağlamış. Sanki ikinci thread'in stack'in en altında global'lar varmış gibi. Herkesin kendine özel global'ları var. Söylemeye çalıştığı şey esasında global falan kullanma, hepsi lokal olsun diyor. Bu şekilde yapmış.
Hocam
Global
peki
kullanmak tehlikeli bir şey.
iki thread arası ortak bir değer varsa onu nasıl olur?
İki thread arasında ortak bir şey kullanmak istiyorsan tabii ki o zaman bunu yapacaksın zaten. Ama o zaman onu yapan adam hiçbir zaman ya ben elini değiştirmiştim birdenbire farklı oldu falan demez. Başkası ona göre kod yazmıştır. Zaten ona interprocess communication deniyor, tamam mı? Onunla ilgili zaten konuşuyoruz. Orada da sıkı problemler var. Yani başkasının değiştirebileceğini bildiğin bir şeyler yapabilirsin. İstediğin belki olur. Mesela buraya bir rakam yazacak, bu da buradan okuyacak, onu kullanacak, tamam mı? Consumer, producer, consumer problemi gibi. O başka bir dünya ama senin beklediğin, şurada benim beklediğim neydi burada beklediğim? Ben bu kodu yazdıysam, burada ABC'yi bu fonksiyona yolluyorsam ben burada, bu fonksiyonun ABC'yi stack'te alması lazım. Bunlar benim lokallerim yok yani 100 tane thread de çağırsa bu G denen fonksiyonu, benim thread'imi etkilememesi lazım. Niye? Çünkü her bir thread'in kendi stack'i var. Her birinin lokal değişkeni var. Her birinin işte return adresi falan birbiriyle farklı olacak. Problem yok orada. Global'da da problem çıkıyor. Problem global'larda olmaya başlıyor. Yani global değiştirir, başkası değiştirmez diye düşünüyorsan hata, büyük hata olmaması lazım. Böyle düşünmemek lazım. Tamam. Using threads, library routines. Another problem is here. If you write a library routine, let's say what else? What do I say? str talk, right? Str tokenize. Remember this function? Str talk. You call it more than once, right? You call it first. You give the first string, then you call it again and again to give your tokens. How does it work? It stores the initial parameters in a static variable inside str tokenize, right? Then when you call it again and again, it starts giving you other tokens. So it has kind of a memory, right? Because it uses static memory inside this function. Okay. So these kind of functions are not good for the multi-threading libraries because if I call this function first with some parameters and repeat the call again and again with the other parameters from other threads, so the first call will mess up the execution of the other threads because it has its own memory, it uses the static variables. That's why they say that do not use static variables. Static variables are very bad. Inside static variables inside the functions that I mean. Static variables inside the functions are very bad for the multi-threading applications. Globals are bad, static variables are bad, okay? Static variables are kind of globals actually. So, when you are writing thread-safe applications, do not use globals, do not use any static variables because if one thread changes that static variable, other threads will get affected. Okay. Library routines may be used by more than one thread simultaneously. Not all routines are prepared for this, for example, for this one. Okay. Static variables can be overridden by another thread and must use re-entrant routines. What is re-entrant routine? Re-entrant routine, okay, this is the definition. A routine that can be invoked more than once simultaneously. A function, it is called more than once by different threads at the same time. If the function that I wrote can be called more than once at the same time, then it's a re-entrant routine. So if I have a function like this, integer f, it takes another integer, and it just does this. Return b plus 1. Is this a re-entrant routine or not? Is this a re-entrant? Yes. Why? Because it can be called as many times as you want, or it can be called simultaneously. Because if a thread runs this, okay, it sends a parameter which is pushed onto the stack of that thread, and it just returns b plus 1. There is no problem with this one. But if I have, let's say, a static variable, static integer a, okay, and if I do, okay, and I'm doing this b, if I do this a plus b, then that's a problem. Why? Because that static variable is going to be remembered from call to call, from the next call, okay? If I call this simultaneously by two different threads at the same time, whatever this value is passed will be assigned to A in the first one, and the second one another value will be assigned. And when I switch between those threads, whatever I will return will be some kind of a jump. It will not be what I am expecting. Okay, so with the re-entrant routines, I can use only local variables or dynamically allocated variables. I cannot use globals, I cannot use statics. Okay? So many C library routines do not use static buffers. When you use static buffers like the str tokenize, it uses some static buffer. It is not a re-entrant routine. I cannot do this with the multi-threading application. There are a few simple rules with the multi-threading applications, and some of those rules are: do not use any statics, do not use any globals, do not try to modify any globals inside the re-entrant. Buradan ders. Okay, that's enough for today. Then tomorrow I will start at 10. Okay. Kaçta ders kaçta? 10 demek değil mi?